Hi, I'm Brandon Lipscomb, and today I will be solving problem 6.60. Potential flow against a flat plane, figure P6.60a, can be described with the stream function. Stream function equals A times X times Y, where A is a constant. This type of flow is commonly called a stagnation point flow, since it can be used to describe the flow in the vicinity of the stagnation point at O. By adding a source of strength M at O, stagnation point flow against a flat plane with a bump is obtained as illustrated in figure P6.60b. Determine the relationship between the bump height H, the constant A, and the source strength M. All right. Now our stream function of potential flow against a flat plane was given to us in x, y coordinates, and we want to change it to Cartesian coordinates, which is just r omega. Now to do that, it's fairly easy. You draw your x, y. Here's your line of length r with omega measured from the positive x-axis counterclockwise. And then to get x and y, x is simply r cosine theta, and y is r sine theta. We know this using just trigonometry to find that. All right, now we can rewrite our stream function as A times x, which becomes r cosine theta, times y, which is r sine theta. Now this can be simplified to a r squared sine theta cosine theta. All right, we know we can actually simplify this further using the double angle identity, which is 2 sine theta cosine theta equals sine of 2 theta. All right, so we can divide a by 2 and then multiply the sine and cosine by 2, which keeps our stream function the same, but allows us to use this double angle identity. So before I sub in the double angle identity, I will show what it looks like to change the function into what we can use for it. All right, so this part we can sub in the double angle identity, and it simplifies down to a over 2 r squared sine of 2 theta. Okay, that's our simplified version of this equation in Cartesian form. All right, so now I'm going to pull 3 equations from the textbook. The textbook I'm using is Fundamentals of Fluid Mechanics, the 6th edition. I'm pulling it from page 289, and I'm going to pull the stream function of a source, which is equal to m over 2 pi times theta. I'm also going to pull the relative velocity, which is equal to 1 over r, the derivative of the stream function with respect to omega. Okay. And then our tangential velocity, which is -1 times the derivative of the stream function with respect to r. Okay, I got those all from page 289 once again in the Fundamentals of Fluid Mechanics, the 6th edition. All right. Now we can get our total stream function by adding the source function along with the potential flow against a flat plane to get our picture B with both the source and potential flow. You can just add these together. So our total stream function becomes a over 2 r squared sine of 2 theta plus m over 2 pi theta. Okay, now this is our total for the entire thing. First, we're gonna solve for both the relative velocity and the tangential velocity, but I'll solve for the relative one first. The relative one, 1 over r. I'm just gonna rewrite it, derivative of the stream function with respect to omega. This becomes 1 over r, derivative with respect to omega of the stream function. So I'm just going to pull it over here for a second so I have more room. A over 2 r squared sine of 2 omega plus m over 2 pi omega. All right. With respect to omega, this is a constant and this is a constant. So when we take the derivative, it becomes 1 over r times the derivative, which is a over 2r, because that's the constant in this. The derivative of sine 2 theta becomes 2 cosine 2 theta. Okay. The 2's cancel out, plus m over 2 pi, because the derivative of omega with respect to omega is 1. And then this can be simplified out when we divide by r. Both these becomes the relative velocity is equal to ar cosine 2 theta plus m over 2 pi r. Okay, that is our relative velocity. We will solve for our tangential velocity as well, which is just -1 times the derivative of the stream function with respect to r. Okay, -1 of the derivative with respect to r of the stream function, which is a over 2 r squared sine 2 theta plus m over 2 pi omega. Now this is a constant, there's no r term, so this goes to 0. And this is a constant as well as sine 2 theta. So when we take the derivative, it becomes -1 times 2r, which is the derivative of r squared, and then times the constant, which is a over 2 and sine of 2 theta. Okay. Make the brackets. Okay. This just becomes 0 because this is the whole thing is a constant. There's no r term. And then we can simplify this even further just by distributing the -1. So it becomes, oh, and the 2's cancel out there. It becomes -ar sine of 2 theta. Now the instructions were to determine the relationship between the bump height h and the constant a and the source strength m. Now we can't use the tangential velocity to find h with respect to a and m because there is no m term here, but there is an m term in the relative velocity, so we're going to use that. Now let's start by looking at the definition of a stagnation point. So the definition of a stagnation point is that both the relative velocity and the tangential velocity equals 0. This is because water is coming in both directions, and when they hit here, they cancel out. Now this is at a height of h, right? With the x-coordinate 0. So in xy, it would be x equals 0, y equals h. Now we can translate this to Cartesian by finding the angle here, which we know is 90 degrees, or in radians is pi over 2 radians equals omega, and then r would just be h because it's the distance from the point O. Okay, so we know that in the r omega, or Cartesian form, it would just equal h comma pi over 2 radians. So we know at this point, both relative velocity equals 0 and tangential velocity equals 0. So if we plug in 0 to the relative velocity here and plug in r and omega as h in pi over 2 radians, we can solve for h in terms of a and m. I'm going to do that on the back so I have more room. So let's see, VR equals AR cosine 2, okay? VR equals 0 equals AR cosine 2 theta plus m over 2 pi r. Let me just double check I did that right. AR cosine 2 theta and m over 2 pi. Okay. Now we plug in r equals h and omega equals pi over 2 radians. So we can do that now. We get a h cosine 2 times pi over 2 radians plus m over 2 pi h. Okay, the 2's cancel out. You're left with pi radians, cosine pi radians, which we know is -1 cosine of pi equals -1. Okay, so we can substitute, or we can simplify even further. Negative AH plus m over 2 pi h. So I'm going to move AH to the other side. AH equals m over 2 pi h. Now we want to get h alone, so we're going to multiply both sides by h, getting resulting in a h squared equals m over 2 pi. Now we're going to divide both sides by a to get h alone. Okay, and then we're going to take the square root to just get h, and we get h is equal to m over 2 pi a as our answer. Now we solved for the stagnation point at r equals h, omega equals pi over 2, which we were given in terms of m and in terms of a. Okay. Again, I am Brandon Lipscomb, and I will also show you my signature.